In this part of the lecture, the forced harmonic motion, undamped and damped, will be clarified, and some of the expressions which are linked with the forced motion, how it changes, and it is interesting. And the reference are again for this topic are the same books, book by Mario Paz and the book by Anil Chopra. And you will see that first of all you see the system under the free vibration effect, system under the undamped free vibration, then systems under the damped free vibration. Initially you learn about writing the equation of the motion. So now you will see that what happens when the forces are also acting on the system. So when the force is also acting on the system, you know that the equation of the motion, now the P is not 0. Previously the P was 0. Now the P will not be 0. This exciting force may be of short duration. This is basically called as exciting force also, because this force is not static. This is a time dependent force, P as a function of time. It means that there are two kinds of frequencies. One is the frequency of the force and the other is the frequency of the system. It means that we have to see also the response of the force as a function of the time. We must know that response of the force which is as a function of the time, like a seismic loading or machine loading, like any other loading. We must know that what is the behavior of the force with respect to the time. That we apply to the building. And this is called as the time history analysis of the building. So this is linked with the force vibration, that we apply the force to the structures. It can be a very regular force, periodic force, it can be deterministic force, it can be non-periodic loading, it can be random loading. But now our discussion onward will be on the force system, force vibration. So the response of the system that is subjected to the short duration exciting force is also of the short duration, called the transient response. Damping in the system causes the vibration to decay and the system return to rest after a while. This type of response may be critical because of the low cycle fatigue. So the response to the longer duration force has two components, transient response and the steady state response. So if the force is acting for a longer time, then we have now to see there will not be only a single response of the system, but there will be two kinds of response of the system. One is a steady state response of the system, and other is a transient response of the system. So how can you represent that? Steady state response, I will explain in the next slides that on a single graph, how can you show the steady state response and transient response. Of course, the longer term response, when the force remains for a long time, so as long as the force remains on the system, the steady state response lasts as long. But transient response is due to the initial condition, and this is just due to the initial condition. You can say if you are just checking the response of the system due to the initial force when it is applied and what the system behave, like a free vibration response. So this is a transient response. How you can represent the harmonic force? I told you that it will be represented by the Pt, P naught sine of, here the omega is represented in this chapter, in this slide actually, not in the book, but here I am denoting it like that. Just to differentiate that this frequency is not for the system but for the force. This ohm omega, this is the not the frequency of the system but for the force. So force has also this curve pt. This is a pt as a function of the time. Force is changing with respect to the time. Example for this is unbalanced rotating machine, eccentric mass vibration, generator, mill, paper mill, whatever. So this is a regular vibration of the force. ये regular है pt is sin omega t की वजह से this behavior is seen, where p is not is the amplitude, initial amplitude of that. So a force which is changing its response which is actually changing with time. P naught is the amplitude, sin omega t is its behavior function. Now you can now we will prove some, so I will show you some relationship that when the system is undamped, then how the force vibration behave, and when the system is damped, then how the force vibration behaves. So the undamped system harmonic vibration of the dynamic system is governed by, as the damping is 0, so C is 0. So mu plus ku will be p naught sine of omega t. And when you it has now two solutions. This system has two solutions. One is the solution which is a complementary solution. One is the complementary solution that is obtained by putting pt equal to 0 and is equivalent to the free vibration response of the undamped system and is called as the transient response. एक इसके जो है वो transient response हो लेंगे हम, that we were getting in free vibration. But one response, that is the particular solution that is giving the steady state response of the system, and the particular response is of the form, the steady state system का response होगा, that is g sin of omega t. So we have to obtain the two response of the system. The u है now. First we were only talking about this complementary solution. Now we have to talk for the particular solution. So now when you get the value g value, you take the first derivative, second derivative and sign for it. We take put the value of the u double dot and u, and we get the value of the this and solve this equation, and equal to the p sin omega t. G comes out to be this value for particular solution, and complementary solution we can get from the previous cases for the previous free vibration, because that is the response of the system. So complementary solution is this one and the particular solution is this one. Now we have to determine the constant a and b from this equation. यहाँ से हम initial condition लगाएंगे, u naught initial जो at 0 is u naught, and let's say the initial at time 0 the velocity is v naught. We will put the value initially, let's say a cos of omega t. So at time 0 cos 0 is 1, but time 0 sin 0 is 0. So u naught comes out to be equal to a value is u naught जो है it gives us the a value, and when we derivate this equation, इस equation को आप derivate करेंगे this one, then you can get the v naught value, because the initial condition u dot naught and put it equal to the 0 at time 0, it will give you the v naught value. So this solution is the standard for solving the dynamic equation. All the solutions are standard. First you initialize the conditions, and then you find out the u, then you take the derivative, and get these values at the 0 time. The reason is when the time is 0, many parameters become 0. So only with u first case में आप u निकाल सकते हैं, second case में आप b निकाल सकते हैं, first case में आप a निकाल लेते हैं. So in second case, when the derivative is taken and v naught at initial condition, you put down all the values, because the first two a and b are the transient response, the last term is a steady state response. So putting all the values in this u equation now, this equation, putting the value of a, b, we can get the value of the ut. This is the ut, the response of the system under the effect of the force without the presence of damping. Further simplifying it, we can collect the like terms together, and then we can now the point is that what is this value? The frequency of the machine to the frequency of the system. It is denoted by beta here, and in the book by Mario Paz it is denoted by R, I think. R, there it is denoted by R, and here it is denoted by beta. So omega is the system natural period of vibration of the system, V naught velocity, P naught is the amplitude of the applied loading. This omega is the basically the frequency, natural frequency of the applied force. So ratio of this is beta. So we can get this, we can divide it, you know that what is omega? Omega is k over m. So it means that m is equal to k omega square. So we can replace m by k omega square, and we can compute that k over omega square, because k over omega square. So when we will put the this omega square divided by omega square, this will give the beta square value. So final solution for the response of the system under the effect of the force vibration without damping is this one. This is the solution, and you can put down the values different time to get the response. You will see that without the presence of the damping, the response is like that. इसमें दो पार्ट है ना, फर्स्ट पार्ट जो मैंने बताया, दो पार्ट ये कम्प्लीमेंट्री हैं, और लास्ट पार्ट जो है ये पर्टिकुलर सोल्यूशन है. तो फर्स्ट पार्ट जो है इसका रिस्पांस ऑफ द कम्प्लीमेंट्री जो रिस्पांस है, you see that without the damping it keep on vibrating, and what happened that even till the end the complementary response is there. एंड स्टेडी स्टेट जब आप प्लाट करेंगे, वो इसका स्टेडी स्टेट जो रिस्पांस है, यानी कि सिर्फ अगर आप बात करें कि मैं फोर्स का प्लाट करना चाहता हूँ, तो यू गेट दिस रेड लाइन. तो फाइनल लेकिन जब आप प्लाट करेंगे उसमें ज़्यादा डैम्पिंग इज़ नॉट प्रेजेंट. टुगेदर जब आप प्लाट करेंगे तो ये ट्राई टू प्लाट दिस इन मैटलैब कि आपका जो रिस्पांस है दैट इज़ लाइक देयर इज़ अ सम ऑल द टाइम देयर विल बी सम वाइब्रेशन. The reason is कि उसका damping is not zero, damping is not present. तो damped अगर system हो ना, तो वो system अपना ये जो vibrations है ये ख़त्म कर देता है. When the system is damped, the system ends its vibration with respect to the time ये कम होती जाती हैं अपनी, जो blue color की vibrations आ रही हैं. But in this case you will see कि आपका response जो है वो due to the effect of this is going like that. So this is a undamped vibration response of the system when without any damping and under the effect of the regular force vibration. अब अगर आप इससे फर्दर बहुत से हम पैरामीटर निकाल लेते हैं, ये जो फोर्स वाइब्रेशन है इसमें कई चीज़ें इन्वॉल्व हैं. फॉर एग्जांपल डायनामिक लोड फैक्टर. The dynamic load factor is the ratio of the maximum dynamic deflection steady state वाली to the static deflection. So ratio of these two you can determine by dynamic deflection to the static deflection. So what is the value of the particular solution की क्या थी value response की? You can take that value. This is equal to the P naught over K into 1 over 1 minus beta square. ये है इसका into sin of omega t जो particular solution की थी. And what is the deflection of the static? If the load is static, what is the deflection? You know, P naught over K. Static deflection होती है without the time, when only the force act at only one instant when the time is not involved. So P naught over stiffness, that is a static deflection. When you take the ratio of these two, उसको हम कहते हैं dynamic load factor. So the answer is 1. You can get here the idea that how the static deflection or the dynamic deflection is varying. And what is the amplitude? If the amplitude is 1, it means that it is like some value where both are equal, and when the amplitude is infinity, then you can see the thing that it means that at what value of the beta यहाँ both play करता है role कि beta when the frequency of the force which is applied and when the frequency of the system, जब ये दोनों मैच करते हैं तो वो बहुत क्रिटिकल कंडीशंस है. दैट्स वाई इन आवर प्रोजेक्ट्स जब भी हम जनरेटर फुटिंग डिज़ाइन करते हैं वी ऑलवेज आस्क फॉर फ्रीक्वेंसीज एंड वी ऑलवेज केप्ट आवर फ्रीक्वेंसी ऑफ द राफ्ट जो फुटिंग होती है एंड द फ्रीक्वेंसी ऑफ द मशीन हम उनका रेशो काफ़ी चेंज करते हैं. इफ़ द फ्रीक्वेंसी ऑफ द applied loading which is a harmonic loading and the frequency of the system it matches, then what happens? The system becomes go to the resonance conditions. The amplitude somehow increase erratically, and that can be basically that can result into a damage of the structure, cracks in the structure, failure of the structures. That's why this you have already studied that the frequency natural frequency of the system should not match with the applied loading frequency. So that's why इसमें भी आप देखें कि डैम्पिंग नहीं है. although we have the damped, जो हमारे सिविल के तो स्ट्रक्चर्स हैं मोस्टली डैम्प्ड होते हैं, तो उसमें कुछ बिहेवियर डिफरेंट आएगा, वो इससे आगे हम पढ़ेंगे. ये है कि अनडैम्प्ड सिस्टम में इसका अब आप प्लॉट करें एम्पलीट्यूड. इफ़ यू प्लॉट द एम्पलीट्यूड डायनामिक लोड फैक्टर वो आगे आएगा. एक और भी है डायनामिक मैग्निफिकेशन फैक्टर, पहले पढ़ लें. द एम्पलीट्यूड ऑफ द डायनामिक लोड फैक्टर AD called the dynamic magnification factor. So the coefficient that you studied here, the coefficient that you study here, this one, this coefficient of the dynamic load factor, ये amplitude होगा ना, coefficient will be amplitude of dynamic load factor. This is equal to 1 over 1 minus beta square. So this is called as dynamic magnification factor. This play a key role in deciding the amplitude of the vibration. So if I plot the dynamic magnification factor as a function of frequency ratio, beta is the ratio of the frequency of the force to the frequency of the structure. तो आप क्या देखते हैं कि when the frequency ratio is less than 1, you have somehow positive displacement and keeping on increasing, and when the frequency ratio is larger than 1, it is approaching 0. This value is approaching 0, and when it is 1, the value is nowhere in the graph. It's somehow higher value. It means that the response is infinitely large. Amplification factor is infinitely larger when the beta is 1. Okay, and that state is called as the resonance. That state is called as the resonance. So now you can see that when the beta is less, then the amplification is positive and the system is set to vibrating in phase. When beta is larger than 1, AD become negative. ये larger आएगा इधर. When beta is larger than 1, AD is negative and it is out of phase. So this is for beta. You see that this is now out of phase response. Less जो beta है, is a within phase response. और ये जो green color है, it is a static deflection is shown. So in this way you can see the behavior of the system. Now the numerical or symbolically representation of the response at resonance. कि आप कैसे जो है वो रेजोनेंस पे रिस्पांस निकाल सकते हैं. So this system you can see that general response of the harmonic system, how it is represented. It is represented by this. Now how to get the evaluate the response at resonance. For a simple case, U naught is equal to V naught is 0. Let's say U naught and V naught are 0. We want to get the response of a system with initial conditions equal to 0. So then this is left. And further simplifying it, you can write it like that. Now for beta is equal to 1, the numerator and the denominator are both 0. Beta अगर 1 हो जाता है तो it will be 0. And the displacement become indeterminate because 0 divided by 0 is also infinity. So it means that the displacement will be indeterminate. It is a resonance condition and we cannot compute the value unless we use the L'Hospital's rule, because L'Hospital's the limit principle can be used such that the denominator or the value which is making the function infinity, putting the limit over that it is approaching to the 1 but not 1 actually. So then by putting the limit conditions, you can get the response P naught over K, and then putting the values and solving this limit problem by L'Hopital's rule, it comes out to be this one. So this is the response of the system at the resonance. You can put the values and get the response or the peak displacement of the system under the effect of the resonance. So the response is period. Yes. Yes. Can you see the screen?
Yes, sir.
Yes, sir.
Response is periodic with period of the t is equal to 2 pi over omega, and this is the response. You can see that this was the resonant response, and if you time is equal to 2 pi over omega, and if you plot this response, it is peak response is can be obtained, and then the derivative of response at peak, and further simplifying it. So you can see that for every period increase in the period of vibration, the amplitude is increasing erratically. So this is basically the resonant response, because every time with every increase it is increasing, and the difference between the uh, displacement successive displacement, that is equal to P naught over 2K, 2 pi cos of n pi, or generally you can say that it is P naught over K multiplied by the pi. So every time the response is increasing with the multiplicative factor of pi. So this is the response of the system at resonance, that after some time the it will become difficult to control the vibration of the system. This was the undamped system response that we studied now. Next one is the damped harmonic vibration. So let's have some see the relationship, the modified relationship in case of the damped harmonic vibration.
सर
Yes.
सर जो अभी हमने अनडैम्प्ड सिस्टम पढ़ा है सर, इसमें कोई सिस्टम ऐसा हो सकता है कि जिसकी सर डैम्पिंग कैपेसिटी 0, मतलब सर हर सिस्टम की कोई ना कोई डैम्पिंग कैपेसिटी तो होती है, तो सर ये तो आइडियल केस हो जाएगा ना। जैसे सर हम अगर स्ट्रक्चर का करें तो उसमें अपनी डैम्पिंग कैपेसिटी
मशीन वाले सिस्टम होते हैं, मशीन के जो सिस्टम होते हैं, जो इक्विपमेंट वगैरह बनते हैं, मतलब सिविल इंजीनियरिंग स्ट्रक्चर की अगर आप बात करोगे कि स्ट्रक्चर कोई हो सकता है तो नो, माय आंसर इज नो। बट इफ यू से कि कोई यानी कि वैसे सिस्टम हो सकता है, आइडियल मशीन का सिस्टम, इलेक्ट्रिफिकेशन सिस्टम, मैकेनिकल सिस्टम, तो आंसर इज यस, क्योंकि उन सिस्टम के अंदर जो है वो फ्रिक्शन वगैरह ज़ीरो बनाई जा सकती है। और जैसे होता है कि
सर हर सिस्टम फोर्स सिस्टम हो सकता है लेकिन अनडैम्प्ड सिस्टम नहीं हो सकता है, ऐसे ही है?
नहीं, अनडैम्प्ड यानी कि हो सकता है, सिस्टम भी अनडैम्प्ड हो सकता है, लेकिन सिविल इंजीनियरिंग के स्ट्रक्चर्स रेयरली अनडैम्प्ड होते हैं।
ठीक है सर।
बाकी मैकेनिकल इलेक्ट्रिकल के जो चीज़ें बनती हैं, इक्विपमेंट बनते हैं ना, तो उसमें हैं ऐसे सिस्टम जो वो बनाते हैं, वाइब्रेशन मीरिंग डिवाइसेस और बाकी चीज़ें। Now we will and also we must know about the behavior. जब हम ये करते हैं तो इट्स वी हैव टू नो दैट कि अनडैम्प्ड अगर सिस्टम है तो व्हाट इज द बिहेवियर फॉर नॉलेज पर्पज एंड टू सी द डिफरेंस आल्सो, टू सी द डिफरेंट कर्व्स जो आपने पढ़ी हैं, देखी हैं आज, कि कैसे बिहेवियर आता है, and try to plot these curves in the MATLAB because we could not hand on practice in the class on the MATLAB. In the computer lab we could do it otherwise, but now it's your own basically time that you should give some time to it. So now the damped harmonic vibration I was discussing about. The damped harmonic vibration is basically the complete solution for the damped harmonic vibration is this is a initial solution. You can write C is present now, and this solution can be written in this term because now the system damped free vibration से आएंगे relationship, because previous relationship was from the undamped, now it is a damped system, so U can be represented like that. So putting the value and taking the derivative, the solution of the system, the value of the G1 and G2, and by putting the initial condition, taking the derivative, and at initial condition the values of the U can be determined in this way. This is a particular solution, the particular solution for the system under the damping effect. And now the transient solution we import from the damp free vibration. जो complementary solution है, ये same हम वही import कर लेते हैं और इसमें A और B निकाल, A और B, but we have to compute together. So this is a particular solution for the damped system. This is a complementary which we import from the same undamped for the damp free vibrations. Now put the system together. This is the transient response, this is the steady state response. Now solve for the A and B value. by putting the first A value will be computed at time 0 and putting the U equal to 0, because most of the parameter will become 0 and the A can be computed. And the B value is computed by taking the derivative of this function and then putting it equal to 0 at time 0. The B value can be computed. So it is lengthy, of course, but final solution we are interested that what final response is obtained. So transient response is given by the total response है ये असल में transient नहीं है. The total response will be given by our transient. That's transient response. Putting the value of A and B, you can get this the response. And also this is the response, the particular response. So total response and the sum of this is the response of the system under the damped system. It is a lengthy equation which involve many parameters. Damped vibration आ जाएगी, आप zeta भी आ जाएगा, damping ratio, beta the frequency ratio. So all parameters will be there, and time आ गया, zeta आ गया. So you see that the behavior of the system under the effect of the damping will change. Now if you plot this last जो equation number 8 है, if you plot this equation as a function of the time, you see that for the undamped system there was a lot of vibrations. The total response is shown in the blue color, but when the same values with the same values, when the damping is also added to the system, you see that due to the damping effect, the response, the vibration is reducing and it diminishes at the end. And what happens at the end, that the total response and the steady state response joins each other. And this is the realistic structural response also, कि पहले आपकी vibration ज़्यादा होती हैं, after some time जो आपका response है transient response that diminishes. The reason is the damping ख़त्म कर देगी transient जो response है, and the steady state response which is under the effect of the force जो response है, that remains with the system. So you see that when some machine is started and initially the structure have very high kind of vibration, and when after a few minutes or maybe it is the system then after few minutes the vibration become constant. So the reason is that the disturbed response initially due to the transient response and due to the internal structural effect, damping effect, they are present, and due to the damping later on these are reduced. This is the response of the system. Under the effect of the damped vibration, damped harmonic loading vibration. So damped system under the effect of harmonic loading. We can write the response finally in this way also, a simple way, but The rho value will be quite lengthy here. This is the rho. This is called as the amplitude of the steady state response, and phi is the phase angle. So phase angle is this one, and this amplitude is play a key role. Of course, the amplitude variation, you must know that with respect to the time how the amplitude of the vibration is changing, because this sine omega is basically the function of the curve, but the values depends upon this amplitude. Now if you plot the same parameters which we studied in the undamped system, dynamic load factor, amplitude of the factor. What is the dynamic load factor? I told you that it is the ratio of the dynamic displacement to the static displacement. So if you compute the ratio of the dynamic displacement which is obtained and the static displacement, it comes out to be this one. And what is the amplitude of the डायनामिक लोड फैक्टर, इसको हम क्या कहते हैं? डायनामिक मैग्निफिकेशन फैक्टर यहाँ कहेंगे. तो डायनामिक मैग्निफिकेशन फैक्टर AD, the ratio, the amplitude of this one. So when now we plot the same thing which we plot there in the undamped system, this type of curve was obtained where it was like going like this one and this one. But here what you see that the curve is going increasing and increasing, and then there is no values is seen here, and again the curve decreasing and decreasing. So this is the very important plot which represents the amplitude of the dynamic magnification factor AD as a function of frequency ratio. And what we see is that more is the damping, then the amplitude and the magnification is reducing, but for the less damping, for like civil engineering structure, about 0.1, 0.2, you see the behavior is like that when the frequency ratio reaches 1, the magnification become infinity. आप इसमें 1 पुट कर दें फ्रीक्वेंसी में, एंड डैम्पिंग भी साथ लेकिन इन्वॉल्व है. नाउ डैम्पिंग के साथ है इन द प्रीवियस एक्सप्रेशन ऑफ द अनडैम्प्ड वाइब्रेशन, the damping was not involved. So here the damping is also involved, so it depends upon damping. For larger damping there is no higher magnification, but for smaller damping, when the beta frequency ratio is 1 or not exactly 1 here in this case, closer to 1, we see the resonance condition. So the plot between the beta and the AD show that the AD is not maximum at beta 1, the value of the beta to maximize AD. So not at beta 1 actually. We can get that. How? We can derivate, इसको आप derivate कर दें with respect to the beta, और इस पे आ जाता है आपका, क्योंकि डैम्पिंग की वजह से ना एग्जैक्ट 1 पे नहीं आता आपका पीक इसमें. So beta is 1 minus 2 zeta square, very closer to beta 1 वैसे आंसर आएगा. आप देखिए ना 1 minus 2, और अगर zeta आपका 0.1 हो तो 1 minus 2 into zeta square अंडर रूट कितना आएगा बीटा की वैल्यू? .98 आ रही है, 0.99, यानी कि 0.1 पे 0.99 आएगी, और 0.2 अगर आपके पास हो तो 0.96 आएगी. If the 0.2 is the damping ratio, तो 0.96 value of the frequency ratio, you get the peak response. So that response is basically the response. The plot between show that the AD is not maximum at beta 1, the value of the AD is maximum at this beta. So AD maximum आप ऐसे निकाल सकते हैं. What is the maximum amplitude? This you can simply put down the value of the beta back into the AD formula, and you can get the peak response. So this is very informative graph, because it is telling us that where our response at which frequency ratio. Frequency ratio means the frequency of the applied loading to the frequency of the system. The response reaches the maximum value. And when you plot now the phase angle, जो phi है, if you plot the phase angle as a function of, you see that after 1, the frequency ratio after 1 value, suddenly the phase angle is changing. It's changing the behavior at frequency ratio 1. and when the damping is not present, तो उसका ग्राफ वहाँ नहीं दिखाया था. When the damping is not present, you see that this behavior is like that. When the undamped system, the steady state response is in out of phase with the exciting force beta larger than 1. So initially the phase angle remains 0 for the undamped system. When the frequency ratio reach 1, the response become 180 degree. So basically the response of the undamped system is different, totally different, and this response of the system, of the damped system, phase angle, it can be shown like that. Now the resonance response for the damped system. That what will be the effect of the resonance response for the damped system? So at resonance, the steady state and the transient response, as it is at resonance, you just put the approximately the beta 1 and simplifying the relationship of steady and the transient response. And what you see is that when you plot the resonance response at transient state at resonance, due to the damping effect, it's reducing, but the steady state response of the resonance, it is keep on like that. So at resonance initial phase, the transient response will minimize initial phase, minimize the total response, but when the transient response diminish, जब transient diminish हो जाएगा, the system vibrates with the exciting force but lagging by 90 degree. So system will remain with the exciting force which is lagging by this 90 degree change. And for small damping, the total, अगर आप zeta को भी ignore कर दें, small damping जो है, the second term, and then it will be the total response in case of the damping can be seen here. But it is seen that in case of the damped system, the resonance response is relatively different than the undamped system, of course, and the amplitude of the vibration is lesser than the undamped case. So this is the curve that can be plotted for the resonance. For the, you can say, the steady state amplitude and envelope curve. This is seen for the at the resonance, the structure will behave like that. And with changing the value of the damping, lesser is the damping value, you see the more amplitude of vibration, and for higher value of the damping, the lesser amplitude is seen. So amplitude ratio, it can be computed by the number of cycles. After certain cycle, the ratio becomes same. After certain cycle, the ratio of the amplitude, successive amplitude, या जो ratios हैं, you see that initially it change change is quite high, but later on it become constant. So this is the response of the system under the effect of the resonance. In the next part of the lecture, we will continue this discussion further, the response, after a short break, and then we will see few problems related to this topic. Thank you very much.